And now I'd like to continue the list of basic properties of the density matrix. And following sort of a similar structure as the one that we had when we talked about the basic axioms of quantum mechanics, the next topic is measurement. And there are two aspects to it. The first aspect is when we measure an observable A with eigenvalues AI, we ask what is the probability for finding a certain one of these eigenvalues AI. So we ask what is the probability of obtaining in the measurement eigenvalue AI in a state, in a mixed state that is described by a density matrix rho. I had already alluded to that on the previous page. We know, we had discussed earlier that the probability of finding a certain eigenvalue is given by the expectation value of the projector onto the eigenspace that is associated with that eigenvalue. And that's true for in the case of pure state, and that carries over to the case where we have a mixed state. Now the expectation value of the projector in the mixed state rho, that is like any other expectation value in a mixed state given by the trace of density matrix times projector. This is one aspect of measurement. The other aspect of measurement is what happens to the state after a measurement. Remember, in the case of a pure state, when we measure a certain eigenvalue AI, then after the measurement, the system is in an eigenstate of that is associated with that eigenvalue. So the vector in Hilbert space gets projected onto the eigenvector, or in case it's degenerate, the eigenspace associated with the measured eigenvalue. What happens now if we have a mixed state? Also in the case of a mixed state, the state after the measurement is generally different from the state before the measurement. So again, post-measurement, we have a change of the density matrix. If previously we have density matrix rho, then after measurement of the eigenvalue AI, we have a different density matrix. And this density matrix is given by it's the original density matrix rho, again projected onto the eigenspace that's associated with the measured eigenvalue. Now in the case of a density matrix, how does this projection work? We multiply rho with the projection operator from both the left and the right. So it gets sandwiched between two projection operators. And then, as in the case of a pure state, we have to ensure that after this projection, the density matrix, the state, is still normalized. In the case of a mixed state, this means that the trace of the new density matrix must still be equal to 1. And we ensure that by dividing by the trace of rho pi. This rule for updating the density matrix after a measurement is known as the Lüder's rule. I would like to give you a little motivation. I don't want to prove that rule, but I want to give you a little motivation why it looks like that, why it has that structure. Remember the update rule for a pure state. In the case of a pure state, we had initially a state psi, and post-measurement, this psi gets projected onto the subspace associated with the measured eigenvalue, and then it's normalized by dividing by the square root of psi pi psi. Remember also that we said a pure state can be described by a very special kind of density matrix, namely a projection operator. So instead of a vector psi, we can also describe the pure state by a projection operator, p psi, which is equal to psi psi. Now, what happens to this projection operator after a measurement? Well, we have to update both the bra and the ket in this projection operator. So we have both the ket and the bra. To both the ket and the bra, we have to apply the projection operator. So we have a pi from the left and we have a pi from the right. And in both cases, we have to divide by the square root of psi pi psi. Now, if we have 2 times the square root, then it's like 1 over psi pi psi. But then we can say pi psi psi pi, the psi psi in the middle, we remember that's the projection operator. So this is nothing but pi p psi pi. And then in the numerator, this expectation value of pi in the state psi, we can also write with the help of a projection operator. We can write that as the trace of p psi pi. And now remember from last week what happens when we go from a pure state to a mixed state. We go from a projection operator to a density matrix. The density matrix generalizes the projection operator. So here to generalize, you go from a pure state to a mixed state by replacing the projection operator p psi by a density matrix. And now you see the 2 expressions for the update of the state after a measurement. They have exactly the same structure, only that rho, so the projector has been replaced by rho. And now, following the structure of our axioms of quantum mechanics, the third issue that we have to cover is time evolution. We have, under a time evolution, an initial state rho, an initial density matrix rho at time 0. After time t becomes a density matrix rho of t, and this is given by the unitary time evolution operator u of t acting on the initial state rho of 0 from both the left and the right. On the right we have u dagger of t. That's the expression for the time evolution after a finite time t, or the differential form of that is d over dt rho of t is given by minus I over h bar, and then the commutator of the Hamilton operator with rho of t. You can motivate that in exactly the same way that I just motivated the update rule after a measurement. You can consider the special case where the density matrix is a projection operator when it's a pure state. So then rho is just equal to psi psi. You know how a pure state evolves in time, namely by applying a unitary evolution operator to it. Again, you must do that. You must apply a unitary evolution operator both to the bra and the ket in this projector, so from the left and from the right. For the ket, you have a U, and for the bra, you have its Hermitian conjugate, a U dagger. So you get a U from the left, a U dagger from the right. And this generalizes then from projection operators to density matrices, and you have the structure that I just showed you. You know that for a pure state, psi is transformed after time t. It's transformed to u of t psi 0. So the initial psi at time 0 evolves in this way. This means that the projection operator at time 0, this is psi at time 0, psi at time 0. Well, this evolves in time to u of t psi 0. So this is the time evolution of the ket in this projector. And the bra in this projector also evolves with this unitary time evolution operator, only that since it's a bra and not a ket, you have to apply the adjoint u dagger of t. And then again you replace here the psi psi in the middle. This is nothing but the initial projection operator. So you see the structure here. You see the initial projection operator, p psi at time 0, is transformed after time t to u p u dagger. And then when going from a pure state to a mixed state, you replace the projection operator p psi, you replace by a general density matrix, and then you get the structure rho goes to u rho u dagger. And that's the form above. And now you may wonder, how do you obtain this differential form with the commutator, with the Hamiltonian? This is something that I would like to give you as a homework. It's a good exercise to familiarize yourself with working with these density matrices. These are the important properties of density matrices. Next, I'd like to move on to the second reason why you have to work with density matrices. The second reason is that density matrices arise when you look at subsystems of large systems. Before we discuss that, we need some basics about composite systems, systems that are composed of several parts. Let's say we have a system that is composed of n parts, n constituents. That is also called an n-partite system. That could be, for example, a lattice of spin, a collection of spins, of n different spins. If you have spin 1/2, then we saw last week each spin 1/2 is described with a two-dimensional Hilbert space. But now you have n such spins. Each individual spin is described with a two-dimensional Hilbert space. But of course, for the collection of n spins, you need a larger Hilbert space. Let's start with the basis vectors in this larger Hilbert space. Well, if the first constituent, the first part of your system, has basis vectors I1, this is a basis in H1. This is which is the Hilbert space of the first constituent. So if you just had this one constituent, then your basis in the Hilbert space would be the I1. But now you have a second constituent, a second part, component of your system. And this second component is described in another Hilbert space. By itself, it's composed in another Hilbert space, H2. And in this second Hilbert space, you have a basis, I2. Now, the combined system is described in a larger Hilbert space. And this larger Hilbert space has basis vectors I1, tensor product with I2. Sometimes this tensor symbol is omitted, and one just writes the product of ket I1 and ket I2. So, for example, if you the first component is a spin 1/2 with basis vectors up and down, then you would have in the Hilbert space of this first spin, you would have basis vectors spin up, spin down. And the second component is also spin 1/2, and the associated Hilbert space also has a basis spin up, spin down. And then for the combined system of the two spins, you would have 4 basis vectors, namely the 4 possible combinations: spin up, spin up, spin up, spin down, spin down, spin up, spin down, spin down. Yeah? So it's a product. The basis vectors in the combined Hilbert space are simply the products, all the possible products of the basis vectors of the individual Hilbert spaces. Now, if you have more than 2 components, then this just continues, and you multiply all the basis vectors up to the nth system. What is the dimension of the total Hilbert space? Remember the spin example, the 2 spins. Each individual spin is described in a 2-dimensional Hilbert space. Now we have 2 spins, and we had 4 basis vectors in the combined Hilbert space. Up, 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 down, down, up, down, down. So the combined Hilbert space is 4-dimensional. When we generalize that, we have n constituents. The Hilbert space of the first constituent has dimension d1. The Hilbert space of the second constituent has dimension d2, and so on, up to dn. Then the dimension of the total Hilbert space is the product of all these dimensions. It's d1 times d2 times and so on, up to dn. It's the product of the dimensions. And the total Hilbert space, let me denote that by the calligraphic H, is the tensor product of the individual Hilbert spaces. So these are some basics about the Hilbert space of the composite system. Its basis vectors, its dimension. Let's now move on to states of the composite system. Let's consider the case where the individual systems are all prepared in a pure state. So let's consider the situation where the individual systems are prepared in respective pure states psi I, where I goes from 1 to n. What is then the state of the total system? It's just the product of these respective pure states. It's, as in the case of the basis vectors, the composite system is then in a pure state psi, which is nothing but the product of the individual pure states. In the Hilbert space, you have a scalar product, an inner product. You have the same in the case of the composite Hilbert space. You have an inner product. Consider the case where, for simplicity, we just take two components here, two constituents, so n equal to 2. Imagine that you have two pure states of the total system. One pure state is the tensor product of phi 1 and phi 2. Yeah? So subsystem, the first subsystem is in the pure state phi 1, the second subsystem is in the pure state phi 2. This means that the composite system, the total system, is in the pure state phi 1 times phi 2. This is one pure state. The other pure state is the state where the first subsystem is in the state psi 1 and the second subsystem is in the pure state psi 2. So the total system is in the product state psi 1 times psi 2. And now I want to take the inner product of these two pure states in my composite Hilbert space. The way I calculate that is that I simply take the scalar products individually of the respective subsystems and then multiply them. So the result is the scalar product of phi 1 with psi 1. That's the scalar product in the Hilbert space of the first subsystem times phi 2 scalar product with psi 2. That's the scalar product in the Hilbert space of the second constituent. And you can convince yourself, maybe this becomes another homework problem, that this scalar product in your total Hilbert space satisfies all the properties that you expect from a scalar product. It also ensures that states are properly normalized. So if you take the scalar product of a state with itself in the total Hilbert space, and the state is a product state, and the states of the individual subsystems, the pure states of the individual subsystems are normalized to 1, then the composite state is also normalized to 1. So we've learned how we compose the Hilbert spaces, we've learned how we compose pure states, we've learned how we calculate inner products. We still have to talk about observables, or more generally about operators, in this composite Hilbert space. So we have to talk about the tensor product of operators. So we have to ask what we mean by, say we have an observable, or more generally an operator A1, acting in the Hilbert space pertaining to particle to constituent number 1. We have an operator in the Hilbert space of constituent number 2. up to constituent n, the last constituent, and we take the tensor product of these. The result is an operator which is now acting in the Hilbert space of the total system. And we have to define what we mean by this tensor product. And it's defined by the way it acts, by its action on a pure state in the composite Hilbert space. So when we have this operator acting on a product state, psi 1, psi 2, and so on, psi n, then we obtain the result by having the individual operators in this tensor product acting individually on the pure states in the product state. So this is the same as A1 acting on psi 1. Now this gives a vector in the first Hilbert space times A2 acting on psi 2. This is a vector in the second Hilbert space times and so on up to An acting on psi n, which is a vector in the last Hilbert space, the last constituent. So we have here vectors in the respective Hilbert spaces of the individual constituents, and we combine them with the tensor product, and this gives a vector in the total Hilbert space. And with this rule, sort of how a tensor product of operators acts on a product state in the total Hilbert space, this defines the tensor product of operators. One last aspect that I would like to add, and then the list is complete, is the trace of a tensor product. This is something that plays a role in statistical mechanics. That's why I want to add it to this list. When I have two observables or two operators, A and B, acting in the Hilbert spaces of two different constituents, I take the tensor product of these two operators as defined above, and then I take the trace of that. Then this equals the trace of A. Now, on the left-hand side, I have the trace in the total Hilbert space, because it's the trace of an operator which is defined in the total Hilbert space. On the right-hand side, I have just the trace of A, and here the trace is defined in the Hilbert space of the first constituent, because A is an operator in the Hilbert space of this first constituent. I have the trace of B, that's defined in the Hilbert space of the second constituent, and I multiply the two. And the product of the two gives me the trace of the tensor product of A and B. And this is again a problem on your next problem set. I will ask you to prove that. Let's consider a very simple example, the simplest example for a composite system is a system composed of two-level systems, two spin 1/2s. So I have a spin 1/2 which I call spin A. I have another spin 1/2 which I call B. And now I don't look at them individually, but I consider the two spins as a composite system. What are the basis vectors? Now the first spin, the spin A, has basis vectors spin up and spin down. Likewise, the second spin. So the total system composed of the two spins has 4 basis vectors, namely first spin is up and second spin is up. First spin is up, second spin is down. First spin is down, second spin is up. And both are down. To make life easier, I wrote this now without this tensor product symbol. In fact, I would like to phase out this symbol to be a bit economical with the writing. Well, sometimes when I want to emphasize that it's a tensor product, I may still use it, but I will become a little bit inconsistent because I'm lazy. Now, the composite system has these 4 basis vectors. This means that any pure state of the composite system can be written as a linear combination of these 4 basis vectors. And therefore, the Hilbert space of the composite system has dimension 4. So the dimension of the Hilbert space is simply equal to 4, which is the product of the dimensions of the individual Hilbert spaces, 2 by 2. 2 times 2. All right, let me now consider a special pure state of the composite system. Consider the following pure state of the composite system. Psi, and I'll use the subscript AB to indicate that this is a pure state of the combined system of A and B. As we said, this can be any linear combination of the 4 basis vectors, and I would like to consider one particular choice, namely the linear combination 1 over square root of 2, and then spin up A, spin up B, plus spin down A, spin down B. This is a possible pure state of the composite system. Now, let's assume the system is in this, the composite system is in this pure state, but imagine that you are only interested in the properties of the first of the 2 spins. So you want to calculate expectation values only of observables that refer to the first of the 2 spins, that refer to spin A. So you want to calculate, or you seek the expectation value of an observable that relates to A only, to the spin A only. Let me call this observable X, and let me give it the subscript A to indicate that this observable refers to the first spin only. How do I have to calculate that? Well, in a pure state, I have to sandwich it between the state vector psi. So I have psi AB, observable x, psi AB. The pure state is this superposition that I wrote above. Let's multiply this out, it's bracket, and we get 4 terms. We can take a 1/2 in front, and then we get. Now I abbreviate my notation even further. I write up, meaning it's the product of spin A up and spin B up. XA spin up, spin up. Then we have spin down, XA spin down. And then we have mixed terms. We have spin up, XA spin down. And we have spin down, XA spin up. These are all the possible combinations. Let's pick one of these. Let's pick the first of these contributions. And let's look at this a little bit more closely. Now I go back to sort of a more precise notation. I say this is spin up A, spin up B, XA, and then I have spin up and B and spin up A. Now we know observable X refers to spin A. So it acts in the Hilbert space of spin A. Here we have a scalar product of 2 vectors in the total Hilbert space. The first vector is the product spin up A, spin up B. And the second factor in the scalar product is the XA acting on spin up A, and I will draw here an extra bracket to make clear the XA acts on the basis vector relating to A only, and it doesn't do anything, it doesn't have any effect on the basis vector spin up B that relates to the system B. Okay, now we can use the property of the scalar product in the total Hilbert space. We can say this is the scalar product of spin up A with XA spin up A. Yeah, so we take the scalar product in the A Hilbert space only. And then we take the scalar product of the vectors in B Hilbert space. This is spin up B, scalar product with spin up B, and we simply multiply the two. Now spin up, the second factor, spin up B, scalar product with spin up B, scalar product of a basis vector with itself is equal to 1. So this is simply equal to spin up A, XA, spin up A. So thanks to the rules for calculating the scalar product in the combined Hilbert space, and thanks to our assumption that the observable XA relates to subsystem A only, we can evaluate this particular expectation value. We can reduce it to an expectation value that we calculate only in the Hilbert space of spin A. We can apply the same logic to all the other terms appearing in the square bracket. And we will find that this term here, in the same logic, is equal to spin down A, XA, spin down A, and the basis vector spin down B has disappeared. And finally, these two terms here, well, there, what we will find if we apply the same procedure to these terms, we will obtain a factor which is the scalar product of spin up of basis state for B, scalar product with spin down basis state for B. But these are orthogonal to each other, and they give 0, and therefore these two terms, they are equal to 0. So what remains in the end? In the end, we have for the expectation value of XA, we have 1/2 spin up A, XA, spin up A, plus 1/2 spin down A, XA, spin down A. The two expectation values, the expectation value in the spin up state and the expectation value in the spin down state, we can write again with the help of a projector. So we can write the first of these two terms as trace, as 1/2 trace projector onto the spin up state of spin A times XA. And the second expectation value that appears here, the expectation value in the spin down state, we can write as trace over projection operator onto the spin down state of A times XA, and then we have the 1/2 in front. So we can write the expectation value for the observable XA in this form. And you recognize that, again, the expectation value of this observable XA has the structure, it's the trace over something which is in this round bracket times XA. And this something in the round bracket is the effective, or the so-called reduced state of spin A. This is row A. And it's a linear combination of projection operators. And that's something that we had encountered before. Remember our two different experimental setups for a source emitting spin 1/2. This corresponds to the situation of the second experimental setup, where with probability 1/2 you emit spin up, and with probability 1/2 you emit spin down. And we described that with the density matrix, which was 1/2 times projector spin up plus 1/2 times projector spin down. We have exactly the same structure here. So this is the so-called reduced state of spin A, and it is a mixed state. It's no longer a pure state. That's what I meant when I said that when you describe subsystems of larger systems in the way that we're doing here, where we calculate expectation values of observables that relate to a subsystem, then inevitably we run into mixed states, because the reduced state of a subsystem is a mixed state. So this is mixed. This is reason number 2 why we need mixed states. I would like to make a little side remark here, which strictly speaking has nothing to do with statistical mechanics. It's more a topic in quantum mechanics. You may have heard this before, but I think it's part of the general education of a physicist that you've heard of the notion of entanglement. The German word for that Schrödinger coined is Verschränkung, verschränkter Zustand. What we've seen here is if you have several subsystems and all the subsystems by themselves are in a pure state, then we had said in our general discussion of composite systems that then the composite system is also in a pure state. And the pure state of the composite system is simply the product of the pure states of the individual subsystems. So there is a logical implication from left to right. But there's no logical implication from right to left. Because in the example that we just saw, the composite system was in a pure state. It was this superposition state of spin up, and spin down, spin down. But the subsystem A had to be described with a mixed state. The subsystem A was not in a pure state, but in a mixed state. And whenever this is the case, whenever the total system is in a pure state, but at least some of the subsystems are not in a pure state, are in a mixed state, then one says that the subsystems are entangled. Yeah? So if not, then one says that the subsystems are entangled. And this is a genuine quantum phenomenon. In classical mechanics and in classical statistics, you do not have entanglement. When classically a composite system is in a pure state, or the classical analog of a pure state, meaning that you have maximum information about the system, then automatically you also have maximum information about all the subsystems, and all the subsystems are also in pure states. Okay, so this was a general side remark for your general education. And now I would like to return to density matrices. What we've seen so far is that when you have a composite system, you describe subsystems, then inevitably you encounter mixed states. So another reason why we have to introduce mixed states. And we started from the assumption that the composite system is in a pure state. But it may happen that already the composite system itself is in a mixed state. Yeah, so the general state of a composite system may well be also a mixed state. Now, one says that if the density matrix of the composite system is the product of the density matrices of the subsystems, in that case one says that in this state the two subsystems are statistically independent. If, on the other hand, the state of the combined system is not a product state, then one says that the systems are correlated. And the correlations between the systems, they can be classical correlations, and they can also be quantum correlations, i.e. the entanglement that we just encountered. Let's look at an analogy in classical probability. Let's consider two random experiments. A and B. A and B are two random experiments with respective possible outcomes, AI and BJ. So to be a bit concrete, a bit more specific, let's say you have, you flip a coin and at the same time you toss a die. Yeah? Würfel, you toss a die. These are your two random experiments. The first random experiment, the coin has two possible outcomes, heads or tails, and the die has 6 possible outcomes, 1 to 6. Now you can consider then the probability for the combined outcome AI and BJ. So for example, the probability that my coin shows heads and my die shows 3. If the two experiments are statistically independent, then this probability simply equals the probability for heads times the probability of the specific face of my die. So in that case, the two random experiments are statistically independent. If this is not the case, then my two random experiments are correlated. So if there's a secret mechanism that, depending on the result of my coin flip, manipulates the die and it affects the probabilities of the toss of my die, then the two random experiments are correlated, and it's not simply a product. Now, in this analogy that I just indicated, this is classical probability. And there you can have situations where random experiments are correlated. And these are classical correlations. And you can have the same in physics. Consider the coin and the die as two physical systems. And I describe the two physical systems with respective states. And the states are analogs of the classical probability distribution. So the analogy is between physical states and probability distribution. And if I have a statistical correlation between the two random experiments, then these correlations are mirrored in the state that I assign to the two systems. And these would be classical correlations. In contrast, the entanglement that we found in the example of the two spins, this is an example for quantum correlations. This is an example for a type of correlation that has no classical analog, that has no analog in classical probability theory. The important message that I wanted to give here is really the distinction between the case where you have no correlations at all, where the two systems are statistically independent. In that case, the density matrix of the composite system is simply the product of the individual density matrices. Just like in the case of pure states, the pure state of the composite system is just the product of the pure states of the subsystems. That carries over to mixed states. When you have no correlation, it's just the product of the two. And whenever there's some kind of correlation, be it classical or quantum, it's no longer the product of the two density matrices.